Welcome to this course C-based VLSI design. In today's class, we are going to discuss the C-based VLSI design with an example. So, in the previous class, we have discussed the overall that C-based VLSI design flow, and we have already discussed that whatever the IC or integrated circuits you design, it goes through different synthesis steps like high level synthesis, logic synthesis, physical synthesis, then finally fabrication and packaging, right. So, this is something is the overall flow, and we have already seen that because of this large number of transistor present. So, the designing circuit at the transistor level was not is impossible. Then we go for higher abstraction level, which is basically the gate level. So, then you design your circuit using gate level and then use automation tool or software that will convert that gate level circuit into transistor level circuit, right. And then the whole design process goes further abstraction. In the further abstraction is basically the register transfer level design. So, in the register transfer level design, you design the circuit is more abstraction level in terms of the register transfers, and then you use the logic synthesis tool, which is another kind of software which will convert those register transfer level design into automatically into gate level design. Right. So, that was the standard the EDA automation flow, but with the complexity growing and more component is coming, and that and even designing certain things at the register transfer level becoming difficult because of certain parameters or optimization goal like power, area, timing and all, right. So, then the whole design process go one level up, one more abstraction level up, and which is called high level synthesis, right. And what this is something is very interesting, because now so far whatever the design you are talking about, this register transfer level or gate level or transistor level, we have clock, you have reset, all the hardware components are there, you have to break your head on the hardware side. But this high level synthesis brings the revolution, because now you can design your circuit at the C or higher abstraction level like code like C, C++, Python, Simulink, MATLAB and so on, System C and so on, and then you use a software which is called high level synthesis, which is something convert those C code into this RTL. So, this is something very interesting, because you have the input which is not hardware at all, there is no clock, there is no time, it is untimed behavior which is sequential in nature, and this hardware is basically facial, right. So, everything is parallel. So, you have a sequential behavior which is executing top down manner, and now you are converting those particular design into a special design hardware. How you bringing clock, you are bringing all other hardware integrators, right, register, RAM, ROM, everything, right. So, this is something is very interesting, and that is something is the focus of this course, which is that is why we are talking about this course is C-based VLSI design. That means, I am taking a C behavior, C is a representative of a high level behavior, and then how we convert this this particular C code into equivalent register transfer design or an hardware. Okay. So, and then from that RTL you can again use apply logic synthesis for convert into RTL to gate level. From using physical synthesis you convert into this gate level design to transistor level and so on, and then we will get the this is the overall C-based VLSI design flow. Since this logic synthesis and physical synthesis things are more or matured, and is we have well established tool in this domain. So, I am not focusing on those things in this particular course, rather the focus of this course is on the first part, how we convert the C code into register transfer level design. Obviously, in the subsequent part of the course at the later stage we will follow, we will briefly introduce what is logic synthesis, what is physical synthesis, but I am not going to go into detail of those particular topic in this course. Rather, my focus of this course will be particularly in that high level synthesis, right. That is why this course is named as C-based VLSI design, and specifically C to hardware conversion is the topic of interest of this course, right. So, and this is something, this high level synthesis is something is gaining lot of interest in the design houses. So, you can see all the EDA major EDA vendors like Synopsys, Cadence, Xilinx, everybody has a high level synthesis tool as a commercial tool, which is you can buy or you can use for your development of hardware from C component, C or C++ behavior, right. And obviously, we have understood the advantage of this higher level of abstraction, that it basically reduces the overall design cycle. And it's actually enables you for design space exploration. You have possibility of fewer errors because your design size is smaller at the C level, you need less verification time because you verify your specification at C and then you can use it, you can convert into subsequent stages, and also you can apply many optimization at the higher level of abstraction. So, these are the unique benefits that high level synthesis brings in the electronic design automation flow, right. So, and because of this advantages, if you look into this current industry, out of top 20 semiconductor companies, they are 14 is using this VLSI, this high level synthesis tools, or they design certain component of their big SOCs using this high level synthesis tool. Okay. So, that is why this particular topic is so important and is something has a immense potential, because if we can have a very robust tool, high level synthesis tool, which is can convert this high level behavior into some efficient hardware, then it can have a very, it has a huge importance in the context of this electronics design automation, right. So, that is why this particular topic has a huge potential and is of interest of this course, and this is something is still maturing, right. We do not have any very robust tool, or we cannot which can compute still it is not maybe not comparable with handwritten RTL, because once a expert designers write something in the hand an RTL directly, that may be much more faster or much more efficient than the RTL generated by high level synthesis tool. But the last 20 or 25 years research on this high level synthesis make lot of advancements, and because of that this huge change is coming, that 14 semiconductor industry still using now are using have a confidence to use this high level synthesis tools. Okay. So, what I am going to do here in this course in today's class specifically is we understand that high level synthesis is basically taking a C code and convert it into a register transfer level design, but how, right. So, we should actually try to go into little bit deeper on that particular topic. Is okay, we have a C code which basically you have a if else, you have for loop, you have branch, you have this basic block operations and so on, and then you have a register transfer level design where you have this clock, you have registers, you are assigning the registers, you have a controller FSM, you decide what will be the next state, you have some data assignments between the wires. So many things are there, right. So, once you have that kind of RTL, how we can generate such RTL from a C code, because it does not have anything, it does not have any clock, it does not have any register, it does not have any control FSM and nothing, right. So, today's class we will try to see in that particular context, right. So, intuitively if we try to realize a C code using a hardware, what will be the steps to be followed to get that. Okay. So, that is the idea. So, here we have taken a behavior like say where we have a while loop and we are doing something and we are say converting into a RTL. You can understand that here there are some register under certain passage of clock, you are assigning certain registers. Here there are sort of wire assignments operations, this is a part of the controller FSM. So, this is just a representative RTL, it is not the equivalent of this behavior, but this is what the conversion is high level synthesis does, and we should understand how it does, right. So, what I am going to do in today's class, that we are going to take this example which is called differential equation solver, which is basically you takes input as x, dx, u and a, and then it basically in a loop you just calculate this u1, u1, x1, and then once your x is equal to or greater than a, it stops and then its output is y. Okay. Let us understand this is something is given to us. Okay. And I want to do the same thing in a hardware. Okay. So, that is something is the high level synthesis is going to do, and let us see how, if I am the high level synthesis tool, how I should do these things step by step. Okay. So, let us try to understand that. So, in the high level synthesis the steps are pre-processing, scheduling, allocation, binding and data path and controller generation. Let us forget these things, let us try to concentrate the conversion steps. Okay. So, we have this behavior which is given to us, right. So, first of all what we should understand, what is the control and data flow in this behavior, right. So, that is something we should understand, and that is given by the CDFG, control and data flow graph. So, you can understand that there is a block here where we are actually reading the inputs, right. You have to read this data, and there is a basic block here which is going to repeat. So, this is my basic block I, and this is a basic block where the series of operation is going to happen and this is going to repeat in the loop, right. So, this is what, and then once this is done, we have a basic block here where we are going to output the y, right. So, this is how the we identify the basic block. So, basic block is basically this the series of operations, sequential operations, there is a control branch, there is no control flow, right. So, this is my basic block, this is one of the basic block where I am going to do the loop body, and this is a basic block where I am going to do the output things, right. So, there are 3 basic block, and then we will add the control flow, because whenever you are doing this, you will always come here, right. So, I am adding this control flow, and then this is, since this is a loop, this is going to be repeated many times, right. So, whenever this condition is true, I am going to do these things in repeat, and once this is done, I should go to this, right. So, this is the control flow. So, this is the basic block. We will come into how the data flow should be represented inside this in the next slide, but this is how the I will can capture the control flow. So, once we are given the behavior, I should identify, the first thing is that I should identify what are the basic blocks in the flow behavior and what is the control flow, right. So, this is what is we will extract first, right. So, this is something we can automate, and there are obviously this modern day compiler can do it easily. So, this will be done first. Now, inside this in this basic block, so we have, now we understand this is one basic block where the input will taken, this is one basic block, and then there is a basic block here just to output y, right. So, this is what is the control flow. So, now what we should understand, what is the data flow within each basic block, right. Since here there is only input operation, there is no dependencies as such, we will not talk about that much, but within this basic block there is some dependency. Okay. So, what we are going to do is we will take each basic block at a time, we will try to identify the data dependency or the data flow within the basic block. Okay. So, the first thing is to be understood that how we will finally realize the whole hardware is, instead of thinking about the whole design at a time, let us concentrate on one basic block at a time, right. So, this should be our approach. Okay. Because once we, if we decide this will be the hardware, so this is my hardware for this will be the hardware for this will be hardware for this, I can combine them and I can get the complete hardware, right. And we will talk about that on more detail. So, this is how. So, basically we will consider one basic block at a time. So, now if you let us see, if I just take this basic block at a time. Okay. So, now we have this basic block and we have these operations. The first thing we have need some hardware, right, that is going to execute this behavior, and you can see here this u is a very complex operation. There are 1, 2, 3, 5 multiplication and 2 subtraction operations and so on, right. So, the first thing I should understand that this is a very complex operation, and if I try to do it, you have to put the multiplier in a chain, right, because here I am going to do 3x, then I will multiply with u, then I am going to multiply with dx, then in the parallel I am going to do 3 into y, right. So, 3 and y, then I will multiply that with dx, and then I will do the subtraction here, and then finally I will do another subtraction from u, right. So, this is how I am going to do this. So, this is the data dependency, right. But the problem here is that if we try to, but in hardware I have to execute this in hardware, right. So, suppose you have, you make these connections like this. So, you add a multiplier 1, 2, 3, 3 multiplier, and then this 2 multiplier in parallel, then there are 5 multiplication followed by 2 subtraction operations going to happen to just to execute this, right. And it has to be completed in a single clock, right, because in the same clock within this time frame all these operations to be executed. And what is the impact of this? If you try to do this, obviously it is possible, your clock, this length will be more, right, because you have need lot of time, because you need 3 multiplier followed by 2 subtraction and so on. So, this length or the clock period will be more, and hence the clock speed will be less. So, the kind of design you are going to get, it will be very slow, right, because you are the clock period is very high and clock frequency is 1 by clock period. So, say for example, if this is 100 nanosecond, so it will be 10 megahertz, right. So, it is 1 by 100 nanosecond, which is 10 megahertz, right. So, if this is taking say 1 millisecond, that means 1000 nanosecond, then it will be 1 megahertz, and it is taking say 10 millisecond, then it will become 0.1 megahertz and so on. You understand that. So, obviously, if the clock period is more and then my frequency will be less and my clock speed will be less, right. So, the first thing we have to understand, once we are going to execute the whole behavior, I cannot execute everything in a single clock, because if we try to do that, then my whole circuit will become very slow. Okay. So, what the first thing comes in my mind, that once I have the behavior, I have to decide how many clock I am going to distribute the operations into multiple clock, and once I distribute, then I can execute this operation in say 4 clocks. Say for example, in given this behavior, I decided to do this multiplier at a time, this 2 multiplier at a time, this 2 multiplier in a time, and then this and this. So, 1, 2, 3, 4, 5. Say in 5 clock I want to do this. Okay. So, if I do this in 5 clock, that means my clock period will be 5 times lesser and my clock will be 5 times faster, right. So, the first thing, once you try to map this behavior into hardware, the first thing is important to understand that realizing even first thing we have to understand that we have to take one basic block at a time, and once we take a one basic block at a time, I cannot execute the whole behavior within that basic block in a single clock, because that is not practical design. So, what first thing we have to understand, that we have to break this behavior into multiple clock, and so that my clock will become faster, right. So, that is something is to do. So, now the question is, there are these operations are there, these so many operations are there, so many multiplications are there, which one, so let us say I decided to do in 5 clock, right. In first clock, what are the operations I am going to do, in second clock, what are the operations I am going to do, in third clock, what are the operations I am going to do, and so on, right. If that was the question, and you have to it cannot be random, that I just put this operation here and here, because in that case your functionality might change, right. So, to identify that this operation to be executed in this clock and this operation in this clock, you need to understand the data flow. For example, the diagram I have drawn here, I cannot execute this behavior in clock 1, right, until these all the operations are done, I cannot do these operations, right. So, this is depend on this operation. So, this operation depends on this 2 multiplier, this multiplier depends on this multiplier, this multiplier depends on this multiplier. So, until this is done, I cannot do this, until this is done, I cannot do this, until this is done, I cannot do this, and so on. So, this is the data dependency. So, we have to identify the data dependency of the operations inside a basic block, right. So, that something is needed. So, we will do that. So, for doing that, first thing what we are going to do is, we will break this bigger expression into 3 address form or more smaller operations. What we need that, because so this is nothing but 3 into x, right, this is this operation, this is nothing but u into dx, sorry, this is nothing but u into u, right. So, this is into u, 3x into u, and so on. So, you need to identify the unique operations or the 3 address operation, because I am going to execute the smaller operation in a clock, not the complete expression, right. So, I have to break this expression into 3 address form. Okay. What the 3 address form? Individual operation. So, for example, here see that 3 into, so I just do this u into dx, which I am going to put in T1, then 3 into x I am going to put it into T2. Then this 3 into y I am going to put it into 3. Then what I am doing, this u into dx I am going to put it into T4. Then I am doing this T1 and T2, right. So, this is my T2 and this is my T1. If I just multiply T1 and T2, I will get this expression, right. So, this is what I am doing here. So, I am just doing T1 into T2. Similarly, 3 and y is basically my T3. So, then T3 into dx I will get that 3 into y into dx. So, this is how I will just break this bigger expression into smaller 3 address form. Okay. And why do we need that? Because these are the unique operation or the unit operation that is to be scheduled. We already understand that I cannot execute the complete expression in a single clock, that will make my circuit very slow. So, I need to identify the unit operations, and this is called 3 address operations. So, this is what is you have to do first, that you break this bigger expression into smaller unit operations, which is called 3 address operation, and then as I mentioned, because to identify which operation to be executed where, you need to identify the data flow, right. So, data dependency, how we can do that? So, this is my 3 address form for this basic block, right. So, this is I am talking about this basic block, right. And then for this basic block, so we have to identify the data dependency. So, here I am doing u into dx and storing in d1, then this is 3 into x is storing in d2, and this is u into dx is for these operations. So, this is how if we just do that, then what is happening, this T5 is basically multiplying T1 into T2. So, now these two operations, this operation V5 depends on V1 and V2. So, this will give you the dependency that until these two operations are completed, I cannot do this. So, if I just you make a node for each operations, and whenever there is a data dependency, that means if there is a variable defined here and it getting used here. So, these two I will add a edge from this node to this node, right. Similarly, I have this T2 is defined here, it is getting used here. So, I am going to add a edge between these two. So, if we just keep doing, then I will get this data dependency. So, this data dependency dictates what operation to be executed in which time step. It makes sure that this operation V8 will not happen in clock 1, it can only happen when all these operations are completed, right. This V9 cannot execute before V4, V4 is done, then only I can do V9. Okay. So, this is what is called data dependency graph. Okay. So, the first thing, if you understand now, given a C code, now what I have to understand, I have to do it, I have to identify the basic blocks. Within the basic block, you distribute this big expression into 3 address form, and from this 3 address form you identify the data dependency for each basic block. So, this gives me the idea how many basic blocks are there, what is the control flow, and within the basic block what are the operations available and what is the dependency among them. Okay. Dependency in terms of read after write, right. So, the read after write dependencies. Okay. So, now the way I should proceed, that instead of taking everything together, if say I will take this basic block at a time, then I am going to take this basic block at a time, and then I am going to take this basic block at a time. I will identify how many clocks I need to complete this behavior, how many clocks I need to complete this behavior, how many clocks I need to complete this basic block, and then you combine this using this control flow, and that will give you the overall behavior order. This is how the things will execute, and so that is something I am going to do. Okay. So, what I am doing here is that I identify this basic block, and then I am going to take this basic block B1 because that has a lot of operations, the others are smaller operation. And then as I decide that I am going to do the scheduling, I will decide how many time step I need to execute that behavior. Okay. So, here say I just decide that I am going to do these operations in time step S1, these are the operation I am going to do in time step S2, these are the operation I am going to do in time step S3, and these are the operation I am going to do in time step S4. So, this is something is satisfying the data dependencies. You can see here that when I am trying to schedule this, both his predecessor operations are done. I am trying to schedule here which predecessors are already available, and when I am trying to do this, its predecessors are already executed, right. So, that means scheduling determine the operation for each time stamp, right. So, that is called, that means it is assigning time stamp to each operation. It determines in which each clock what are the operation going to be executed. Okay. So, this is what scheduling. So, we have understood that within the basic block there are big expressions, I cannot execute in one clock, and I will distribute them into 3 address form. I will identify the data dependency, and then I will assign the operation to the time stamp which satisfy the data dependencies, right. So, if once it is done, I understand that this loop body, right. So, that loop body I can execute in 4 clock, right. So, this loop body I can execute in 4 clock because that is what I have decided, and then since this is a loop, I will just keep doing it every time. So, if the loop execute for 10 times and each time I need 4 clocks, so I need 40 clock cycles to execute the loop body, and let us say I need 2 clock cycle to execute this, and I need clock cycle to execute this. So, total clock cycle needed to execute this behavior is 2 plus 40 plus 1 43, right. So, although this is a C code is given just like this, it need 43 clock cycle to complete the execution. I am just giving a idea that this is how this behavior is going to execute in the hardware, that in the first clock 2 clock it will read this data, next 40 clocks it will just do these operations of the loop, it will just repeatedly doing these 4 operations in the loop, and once this loop is done it will come out and will print the output in 1 clock. So, this is how this particular behavior is going to be executed in the hardware. Okay. So, this is understood, right. So, this is what I am going to overall I understand this particular control and data flow is something is important, and from there I can understand what are the order of the clock and what is the total clock is needed after the scheduling. Okay. So, that is understood, that this is the operation to be executed in time step 1 and so on, right. Now, the question is how this operation is going to execute in hardware, because there is no hardware with me. I just decide that for that for loop or while loop I have given I need 43 clock cycle, but I never decide that where this operation is going to execute, because there is no hardware to me, there is no data path to me. We have to realize that, right. We have to realize the data path. So, now the question is here, how do we going to realize? I am going to consider a multiplier for each such multiplication, then there is 1, 2, 3, 4, 5, 6 multiplier, then I need 6 mult, right. So, then I need 6 multiplier, which is something is obvious. I mean, obviously it is a good solution, it is a solution, but it is not a good solution, because there may be a possibility that I can execute the same behavior using 3 multiplier as well. So, instead of using 6 multipliers, I can use only 3 multiplier to do these things, right. So, the problem that will come to mind is that given this schedule, what is the minimum number of functional unit is needed to execute this behavior. So, that is the problem now, right. So, I have decided that in clock 1 I am going to do this 5 operation, clock 2 I am going to execute these 3 operations and so on, but I never told you that how many multiplier I need to execute this behavior. So, that is what we need to identify next. So, I know that there are 6 multiplication operation is happening across 4 clock step. Now, do we need 6 multiplier, or we can use lesser multiplier to do this, and the answer is it is possible to use a lesser multiplier than 6 multiplier to execute this. So, then the question you are going to ask, how many minimum number of multiplier is needed to execute this behavior, right. So, that is what is called functional unit allocation. To identify the minimum number of function unit is needed to execute this behavior. Next the question is come, okay, so there are 6 multiplication operations and there are you identify 3 multipliers, say for example, but which multiplier is going to do which operation, right. So, there are 6 multiplications, 3 multiplier function unit. So, you have to map this, right, you have to map this multiplication operation to the multiplier, and that is what is called binding. Okay. So, the next step is you identify or allocate minimum number of function unit and also bind the operations of the behavior to the multiplier or the function units. So, that is what is called function unit and allocation and binding, right. So, that is the next problem. Similarly, you have many variables in the program, right. In the hardware there is no variable, right. In the hardware you have memory, registers, RAM and ROM. So, if you have an array, you map that array to RAM. Okay. If you have variables, you should map them into register. Again the same question I am going to ask. So, obviously, in the hardware you need registers and RAM for array, right. So, let us forget now array part, only say think about the variables you have. Okay. So, you have set of variables, let's say in this program you can understand that you have variable like T1 to T8 variables and 1, 2, 3, 4, 5, 6, right. So, 8 plus 6, 14 variables are there, right, in this variable. So, 1, 2, 3, 4, 5, 6 plus T1, T2, that intermediate variables, right. So, now the question is do we need 14 registers, or can I use less number of register to store this? Okay. The answer is yes, you do not need 14 register, because that is the maximum possible thing and which does not give you the best hardware. So, the question or the problem that you should need to solve now, given this variables available and the schedule, identify the minimum number of register needed to execute this behavior or store this variable to this register, that is called register allocation. Okay. And once you have the same once the allocation, say for example, say for this 14 register you identify, you need 10 registers, right. So, there are 14 variables, and say I am giving an example that I need 10 registers. So, I by some algorithm, by some analysis I identify I need 10 registers. So, the question is that again the binding problem, that you have 14 variables, which register will store which variable and which time. So, that something is the binding problem. So, basically once the schedule is done, based on the schedule you identify, the next two problem is the register allocation binding problem and function unit allocation binding problem. Okay. So, that you have to do now, because that is how you actually realize the data path or the hardware, because so far you just decide the clocks, you just decide so far you after scheduling you only know you need 43 clocks to execute this behavior, nothing else. So, now you have to realize, oh okay, I need 43 clocks, but what is the resource I need? So, the resource you have to determine, and resource is basically two type of resource, data path and the function unit and the registers, right. Register to store the variable, function unit to execute the operations. Okay. So, let us consider this register allocation binding problem, how we should do that, right. So, now the question again I am going to ask you how we should do that, right. So, how we can share the register, right. So, for example, if you understand that if there are 14 variables and say 10 register, that means one register must store more than one variable, right. But at a time it can store only one value, right. The question here is that there are 10 registers and 14 variables. Definitely some of the register is storing a variable more than one variable, and obviously at a time it can store only one variables, right. So, that means it is actually for some time stamp it is going to store one variable and other time stamp it is going to store other variable. So, for example, here there are 4 time stamps, right. So, there are 4 clock, maybe one register is needed to store, so which is storing say T1 for this time and say T7 here, right. So, then only it is possible, right. So, that is the problem, that given this schedule how do you identify this minimum registers and their binding. Okay. So, that is something let us understand. We can do this way. So, obviously understand that a register has to share more than one variables, but how to determine that. So, once you write this program, right. So, once you write this program in the C code we just write T1 equal to this and that, right. So, once you write this program we just write this, we never bother about what happened to this T1 after this, right. After this T1 I do not care how this T is happening, right. So, here you understand that this T1 is defined here and it is getting used here, right. So, that is all, and rest of the time I do not need this. So, once this T1 is defined and then it is getting used, after that I do not need T1. In the hardware I can remove that value, because I do not have no use of the T1 for the rest of the circuit or rest of the time. So, let us remove that value from the register and store something else. So, that is how the sharing happens. Okay. And how we should determine? This is determined by the lifetime of the variable. So, that means the time where it is getting defined and where it is getting last use, right. So, for example, you see here T1 is defined exactly at this point at the end of time stamp 1 and it is just used here, right. After that it has no use. So, the lifetime is basically just this, right. So, just at the end of S1 and in S2. So, that is what is represented by this. So, this is the lifetime of the variable. So, if you just think about this T6, it is exactly defined at this point and then it is getting used here. So, the lifetime is this, right. So, this is my T6. So, this is how for each variable I can identify the lifetime. So, this is my T1, the lifetime is only for S2, it is just starting from this. T2 is again it is basically defined here and it is getting used here. So, just the lifetime is here. So, this is how you can identify the lifetime of the variables. So, that is the time where I need that value in the hardware, okay. And then I can share register if their lifetime is non-overlap. That means, if this variable is needed here, I need this variable is needed here, and they do not need in the common time or there is no overlap in their lifetime. So, then I can store them into a single register, right. So, for example, here see T1 lifetime is this T2 lifetime is this, T6 lifetime is this, and they are non overlapping. So, they need in the hardware in different time. So, I can store this T1, T3 and T6 into register R1, right. That is what is the register sharing, and so this is how this sharing happen. So, this is how I will identify the sharing of variables within a register, and hence I can reduce the number of registers. So, if you take this behavior, I can show that I need only 11 registers for these variables, okay. And the sharing is register 1 is going to store T1, T2, T3 and T6, register 2 is going to store T2, T5 and T7, and there is no sharing for the other register because their lifetime is kind of overlapping. For example, U I need for all the time. So, I cannot share it with anybody because it need to be in the register for all the time, and so on say. So, this is what is called register allocation and binding. So, what I am doing here is, after scheduling I identify what is the minimum number of register is needed, and for each register what are the variable can be stored, okay. And the problem here is that the objective is to reduce this number of register and hence improve the sharing, okay. So, this is what the register allocation and binding. The same thing is to be done for function unit allocation and binding. So, what is the idea here, that in function allocation and binding, so I am doing this multiplier here and I am doing this multiplier here. So, they cannot be share the same multiplier, right, because this multiplication and multiplication is happening in parallel in time stamp 1, this 3 multiplication happening in time stamp 1. So, I need different FU, but this multiplier happening in time step 2, this multiplier in time step 2. So, I can share the same multiplier to do this and this, right, because in the time stamp 1 this multiplier is going to do this operation V1 and this multiplier is going to do this this operation V5 in time stamp 2. So, I can do using the same multiplier, I can do this two multiplication because they are actually not happening in the same time, but I need a different multiplier here because this multiplier and this multiplier happening in parallel in the hardware, right. This, so, I need 3 multiplier and I can do this, right. So, I can do this V1 and V5 using multiplier 1, this V2 and V3 using multiplier 2, and this is for multiplier 3, and this also I can do using any of them, right. So, let us say I just do it multiplier 2. So, that means for again I can identify the kind of the time stamp where it is getting used, and then if a multiplier is used in different is happening in different time stamp, I can share the same multiplier, right. So, this is how I can actually identify the minimum number of multiplier needed and the binding, okay. And let us say this is one of the possible binding I have identified for this. So, as I mentioned earlier that I need 3 multiplier for these 6 operations, 3 multiplication operations. So, this is happening here, and this multiplier is going to do this V1 and V5, multiplier 2 is going to do V2 and V3, and then multiplier 3 is going to do V4 and V6, okay. So, this is what is the mapping, and same thing I have to do for adder, right. So, this is I just do for multiplier, I can do for adder and addition and subtraction is same in the hardware. So, I can use the same ALU for that, okay. So, this is what is the next step. So, first what I did, I identify the total number of clock is needed, that is first, because you cannot do everything in a single clock, then it is not feasible. So, I have to do it in multiple clock, and given the behavior I have decided to do it in say 43 clocks, and then to execute that behavior in 43 clocks I have to determine what is the minimum number of registers and what are the minimum number of function units needed, and that is what is called allocation and binding step, right. So, there I am going to identify the minimum number of multiplier, minimum number of adder, minimum number of registers with that. So, once this is done, so I have both available, I know how many clocks is needed, each clock what are the operation to be executed, and that operation to be executed using which function unit and which variable stored in which register. So, this information we have now, okay. So, if you have this information, what I can do is this. So, this is my, I know this is the schedule in timestamp 1, this 4 operations happening, in timestamp 2 this 3 operations happening, and so on. I am not writing for other 2. So, this 4 operation is happening in timestamp 1, this 3 operation is happening in timestamp 2, this 3 operation is happening in timestamp 3, and this operation is happening in timestamp 4, right. So, I just write this V1, V2, V4 and V10 into here, right. So, this is what is happening here, and this V5, V3 and V9 is happening in time V5, V3 and V9 is happening in timestamp 3. So, I just wrote it for 2 clocks. Similarly, S3 and S4 the operations are there, and I know these variables are mapped to these registers and so on. So, this is my register mapping information, and this is my FU mapping information. I need 3 multiplier, and these are the operation to be executed in multiplier 1 and so on, and I need 1 adder to execute all these 4 operations, because you see here there is only 1 addition operation here, 1 addition operation here, 1 addition operation here, and 1 operation. So, these are all in different time step. So, I can just use adder 1 to do all these 3, all 4, right. Same adder to execute all the addition operation. Okay. So, this is the mapping information is available, right. So, then what I can do is very interesting. So, I can rewrite this behavior in terms of register and FU. How? Because I know this T1 is nothing but R1. So, what I am going to do, I will just write R1 here, this U is nothing but R5, dx is nothing but R7, and this multiplier is nothing but multiplier 1, right. So, that means if I just rewrite this, I will get this expression, right. So, this is the expression I am going to do. So, same thing I can do for this and this. So, I will get this. Similarly, I can do for all operations. I just replace the variable using the corresponding register, replace the operation by the corresponding FU from this mapping information. Then I can rewrite this schedule behavior in terms of this. And what is this? This is nothing but RTL, register transfer level behavior. Why? Because here you can see that I have these 2 registers, and in this clock, in clock 1, this will be multiplied and this value is stored in R1. So, this is a transfer of value among registers, right, through some function unit. Okay. So, this is what the transformation from the behavioral code into register transfer level code, right. This is what is the C to RTL transformation. Okay. And this is what is happening for every clock, right. So, I can do the same thing for S3 and S4 and so on, right. So, this is how I replace the operations of the C behavior in terms of registers and the function unit of the data path. So, that means I have now clearly understood that what are the operations to be executed in clock 1, clock 2, clock 3 and clock 4 and so on, and this 4 we are going to repeat, right. This is done, right. So, this till this point. So, I already have, I can rewrite my C code in terms of register transfer level now. So, all this my T1, T2 these things are there does not exist now. I have only R1, R2 everything. I do not have this star plus and all, instead of I have the FUs now, M1, M2, M3 and so on. Okay. So, once you have this, what is missing here? The missing is that is okay, I understand that I have to do this, but I have to make the connection from this R5 to this multiplier 1, R7 to this multiplier 1, and then the output of this multiplier to this R1, then only this operation is possible, right. Unless you make the connections from the register to the FUs to the register again, you cannot realize these things in the hardware, right, and that is what is called data path synthesis. So, given this operation to be executed, they are not connected. I only identify I need 11 register and 3 multiplier, 1 adder, but the connection from this register to this multipliers, connection from this register to this adder and so on, it is not determined yet, right. So, I have to determine that, and that is what is called data path synthesis. I have to make the connections from my components, register to FUs, FUs to register again, and that is what is called data path synthesis. And that step is something very interesting. See here what I have to do in timestamp 1, for each multiplier I have to realize what are the input is coming, right. So, I realize that, say for certain cases, say in timestamp 1 I need R1 and here say R6, and the result will be going to store in 1. So, this is my timestamp 1 operation. In timestamp 2, say I need this R2 here R1 and I need, and the result will be stored here. So, it is basically this FU is doing R1 equal to R1 star R6 in timestamp 1, in timestamp 2 it is doing R1 equal to R2 star R1, in timestamp 3 it is doing this, right. So, that means R2 equal to R1 star R5 and so on, right. So, I can understand what are the register to be connected to the left input of this FU, right, and what are the register to be connected to the right input of this FU. Similarly, the output of the register to go to which are the registers, and remember they are actually time division multiplexing, right. So, they are not in the same time. So, they are in different time, right. So, time 1 I need R1 and R6 and the result should go to R1 and so on, right. So, point here is that given this register transfer level behavior, I can just go by each step and each multiplier and I identify the register inputs. For example, here for M1 I need R5 and R7 in time stamp 1, for M1 I need R1 and R2 for the next time stamp and so on. This is how I can identify the possible register inputs to the FUs, possible register into the FUs and output of the FU to the possible registers, right. Once you have this, what you have to do, you have to make a connection, right. You just need a mux here, right, and you have to put this R1, R2, R1, R2, R1, R4 and R5, right. So, you need a mux for that and this will come here, and you need a controller which will basically control this, right. So, if you this controller is need 3 bits. So, if you give 0 0 0, then this R1 should come here. If you give 0 0 1, then this R2 should come here. If you give 0 1 0, then this R1 should come here and so on. And then if you give this 0 1 1, then this R4 should come here, right. And then if you give 1 0 0, then this R5 should come here and so on. So, that is what is called data path synthesis. You identify the registers that need to be connected to the left input of the FU for different clock, and accordingly you put a mux there and you assign the controls so that the corresponding value can go to that FU in that corresponding, if you give the correct control signal, right. If I give the correct control signal, that corresponding value should go here. Similarly, I have to put a mux here which will go to this, and similarly this value can go to R1. So, for each register R1, R2 and so on, you need a mux at the fire, because this data can come from FU1, also FU2 and come from FU3 and so on, right. Similarly, for R2 also the data can come from say FU1 and say FU2, right. So, you need to put multiplexers at the input of the each function unit. You need to put a multiplexer at the input of each register, and the size of the multiplexers and the exact connection to be made can be identified from this RTL behavior, right. So, best because I have to realize this behavior in the hardware. So, from this behavior I can identify the possible register inputs, and it is also in the time division multiplex, right. So, I have to understand which time which register is needed, and based on that I just put the multiplexer at the inputs, and then and also because one register input can come from various function unit. So, I need a multiplexer at the input of the register as well. So, this is how I will make the connections from the register to function unit to registers, right. So, if I just take this behavior, the behavior I have, this is the data path I am going to get. So, no need to go into detail of the correctness of this, but you can understand this is the multiplier 1 and this data should come from R5 or R1. Similarly, this multiplier input should come from R7 or R2, which you can understand from this behavior. See, for multiplier 1, in the first clock the left input should come from R5, right. So, I just put R5 here, and the next clock it should come from R1. So, I just connected R5 and R1 to the left input. Similarly, for the right input I need R7 or R2. So, I have just connected R7 and R2, and this adder is doing 4 operations in different clocks. So, I need to put this 4 connections. So, that is why this adder inputs are 4, but this multiplier is doing only 2 multiplication, and that is why this I have a 2 in 2 as multiplexers. So, this something optimization I am not going to discuss, but this is how I should make the connections. And here also you can see that register 1, if you understand. So, this register 1 input is coming from multiplier 1 in the clock 1, and register 1 multiplier is coming from multiplier 2 in clock 2. So, I have to make FU1 and FU2 at the input to this multiplexer, right. That is what is happening here, and similarly for register 2 and all. So, if I just go step by step to this behavior, this schedule behavior, I can make these connections, right. So, first I will identify the registers, possible register inputs, and based on that I will make the connections, and finally my data path is ready. So, this data path is ready to execute the behavior clockwise. In the first clock it is going to do this R1 into R5, R1 into R7, in the next clock it is R5 into R7, next clock it is going to do R1 into R2 and so on. So, the data path connections is also done, right. So, I have a data path where the connections from the registers to the function unit and function unit to the registers are done. What else is needed, right. So, this data path connection is over. What is needed, further needed? The further needed is the controller, right, because I know that it is a single bit signal, say S, say CS1. So, if I put CS1 equal to 0, then this input will come and it will go to this, right, and if I give CS1 equal to 1, then this input will come to this, right, to this left input of the multiplier. But I have to determine in each clock which operation to be executed, because in first clock, in clock 1, I am going to do R5 into R7, right. So, I have to give CS1 equal to 0 and this one also 0, right. If I give this, then only this multiplier will do R5 into R7. If I give 0 here and 1 here, then operation R5 into R2 is going to execute, but that is wrong. I do not need that, right, because I need to execute R5 into R7 in clock 1. So, in the first clock I have to give CS1 equal to 0, here 0. I should not give 0 1, right. So, I should give 0 0 for the first clock, and the next clock I need to give this and this. So, I should give 1 1. So, 0 1 and 1 0 is not a valid input for these multiplexers, these two multiplexers. If you give 0 and 1 here or 1 and 0 here, it will do some multiplication, but that is not something I need to do, because I need to do this R5 R7 in clock 1, R1 into R2 in the clock 2. I do not need to do R5 into R2 or R7 into R1, right. So, we have to avoid that. So, that means although the connections is ready, I need a controller. So, that will tell this data path, you do this R5 into R7 in clock 1 and R1 into R2 in clock 2 by giving the control signal 0 0 here and 1 1 here. It never give you 0 1 or 1 0, it do not give that control signal. So, that means I need somebody to monitor or control the operation to be executed in the data path, because this data path can do many operations, but all of them may not be relevant or the correct for my purpose, and so I need a controller. So, that will determine the operation to be executed in that particular clock, and that is nothing but the operation is mentioned, what operation to be executed is given to us. I have to just make sure that controller is executing that operations only, nothing else, right. So, that means the next step is the controller synthesis. So, you have to identify the control signal for the muxes, you need to identify the control signal for this input mux to the registers, you need some control signal for the FU if it is doing say plus and minus, whether it is doing plus or minus, and also you need a enable signal for the registers, because these registers they are connected here. So, it may be that in every clock I am not writing this register, right. So, if I give a enable 1, if the enable equal to 1, then only whatever the data is coming here will update the register. If the enable equal to 0, it will ignore the data. So, for example, say if you see here this R1 is getting executed here and here. So, R1, R2, R3 and R4, right. So, other registers are not getting executed. So, I should put this R8 equal to 0 in timestamp 1, because this R8 is connected from this FU, but I do not want to update this register. So, I must need a enable here to stop this updation of the register in clock 1, because in the clock 1 I need to only update R1, R2, R3 and R4. In the second clock I need to update R1, R2 and R8, I do not need to update R3 and something else. So, I need to put enable equal to 0 in clock 2 and so on, right. So, I need this many control signals, right. So, that is what is called controller synthesis. So, you identify how many control signals is needed, what are the control signal is needed for FU, whether it is doing addition or plus minus, you need the multiplexer at the FU input, you need the enable for the registers, you need the multiplexer at the register input. So, these are the possible control signals, right. So, for the example that I have here, I need only this is doing a plus or minus. So, I need 1 bit here, I need 1 bit here, 1 bit here, 1 bit here, 2 bit here, 2 bit here, and so that means 1, 2, 3 and 4, 7 bits, right. So, I need the 7-bit inputs control signal for multiplexer at the function in input 1, I need one input for the FU, because other multiplier is doing multiplication only. So, there is no control signal needed, every time it will do multiplication only, right. And I have 11 registers, so I need 11-bit enable signal, and there are only 2 multiplexers. So, I need 1 bit here, 1 bit here. So, I need 2 bits for the multiplexer at the register input. Okay. So, that is this is the total control signal. So, I need 21 control bit for my behavior. So, this is the behavior that I am taking about, that example, that for loop, right. So, for that behavior, so this is the final data path, and control this data path I need 21 bits control signals. And what the next thing? So, I identify that I need 21 bit control signals, but each clock what is the value of that control signal, that we have to determine. For example, here I already told you that this must be 0, this must be 0 in clock 1, and in this must be 1 and 1 in the clock 2, right. So, that means each time you have to determine the value of the control signals, and this value you have to assign such a way that this value will execute these 4 operations only, right. So, if I explain, you see here I am doing 1, say 1 means a plus. Since I am doing a plus here, I am putting 1 here, and since every multiplexer is taking the left input, right. So, that is why I am putting all 0, right. So, all the multiplexer inputs are actually 0 here. You see here all are 0, and since I am only updating a register R1 to R3, R4, 8. So, this 4 bits are 1 and rest of the register enable are 0. So, that means in this clock only this R1, R2, R3, R4 will be updated and nothing else, and for this is for the max input of the FUs, and you can see here this R1 is taking from M1 and R2 is taking from M2. So, that is why I am giving 0, 1. So, 0 means it will take from M1, 1 means it will take from M2. So, if I just give this control signal in this data path, it will make sure that in the first clock only exactly these 4 operations to be executed. So, that means the controller controls the data path and makes sure by giving this control signal value that the data path is executing these 4 operations. Similarly, if you give this control signal, it will do these 3 operations in the second clock. You can see here I am updating R1, R2, R8. So, that is why I am giving R1, R2 and R8, and rest of the enable is 0. So, that means I am not going to update the other registers, only these 3 registers I am going to update. And you can see here that I am giving 1 for the marks, some cases 0, 1, this is 0, 1 and 0, 1, and this is 1, 1, because I am going to select the right one. So, so that means if I give this control signal, the data path will execute these 3 operations. So, similarly, I will identify the control signal for S3 and S4. So, now if you come back to this FSM, so I have already determined, say I need 4 control step for this block. So, I need 4 control step, and in the control step this is the control signal, and similarly I have a control signal here, I have a control signal here, I have a control signal here, and let us say for this block I need 2 cycles. So, I need a 2 cycle here, and I need one state for this operation. Okay. So, this is the final controller FSM. Right. So, this is my final control FSM. Here also there should be some control signals, so that it actually do the operation to be done here, and if you just combine this plus this is my data path and this is my controller. So, this will do this operation, right. So, you can understand that this is my final RTL, register transfer level behavior. So, I have given this behavior and I am able to determine this exact data path, able to determine the exact the controller, and these 2 in combination will execute this behavior, right. So, now you can understand that this is 4, and I already told you that it will take 43 clocks. So, the C code is untimed, it just give the input and after you will get the output after some time. So, I do not know how many clocks is needed because it is untimed, but once I execute this behavior into hardware, this data path will make sure it will take, say 43 clock cycle. I am assuming this loop will execute for 10 times, right. So, then it will give you the output. If the loop execute for 20 times, it will be 83 and so on. Okay. So, you understand the overall idea. So, this concludes the class where we exactly say that given a behavior, how this high level synthesis actually goes step by step to realize a register transfer level behavior from a C code. Okay. So, what are the and we have understood that the steps are basically initially pre-processing, which will identify the data path, that CDFG and the data dependency graphs and all, then schedule, do this assigning timestamp to the operation, then you do the allocation and binding where you identify the registers and FUs, and then data path actually gives you the exact data path connections, then the controller give you the exact control signal each time step, and then finally this is nothing but this, right. So, this is the same thing is happening. Okay. So, so this actually conclude the overall process, but what are the interesting thing here, what are the things we will cover here in this course is this schedule is how I am going to do it automatically, right. How can I do this algorithmically, how can I do this to this algorithmically, how given this how can I do these things algorithmically, how given this data path and this information how can I synthesize the controller, right. So, these are the things I am going to discuss in detail in this course, that this is something how it will be automated, what are the various algorithms available there, and what are the algorithm to be applied there, and what are the for a given target objective what algorithm should suits there, and so on, right. So, that should be that I am going to cover in this class in detail, in this course in detail, and I hope you will enjoy this course all these topics. Thank you.